Hi, this is Jishan from JC Tuition, and today we are going through acid-base balance, just a bit of human biochem. So you might remember talking about pH in school as a measure of acidity. The lower the pH, the more acidic solution; the higher the pH, the more alkalotic solution. Well, pH actually means potential for hydrogen, and it can be worked out by taking the negative log, is base 10, off hydrogen. So it's a logarithmic scale. So that means small changes in pH, even from 7 to 6, means a large change in the concentration of hydrogen ions. Also note that it is a negative logarithmic scale. So as the concentration of hydrogen ions increase, the pH decreases, and vice versa. So you could say that pH is inversely proportional to the concentration of hydrogen. The pH of our extracellular fluid is maintained around 7.35 to 7.45. As soon as we fall outside of these ranges, it can get quite dangerous as proteins start denaturing and what have you. This slide here to demonstrate that naturally by metabolism we are constantly producing protons or hydrogen ions, making our internal environment more acidic. And to combat this, we have buffer systems. And by definition, a buffer system is a solution which resists changes to pH when acids or alkali are added to it. So we have chemical buffer systems shown by this diagram here, and these can act immediately. We have our respiratory system, which exhales CO2, as CO2 can make our blood a bit acidic. So someone with more acidic plasma, you'll see them breathing more, just exhale that CO2 and bring their pH back to normal. Respiratory system can correct our plasma pH in minutes. We also have our metabolic or renal system, which can excrete protons, and it can also reabsorb bicarbonate ions. Bicarbonate ions are weak bases, so their negative charge can accept and mop up the hydrogen ions basically and correct our pH. The renal buffer can take hours to days. The chemical buffer systems act immediately. Firstly, we have the phosphate buffer system, which is of minor relevance in our extracellular fluid, but it can accept protons and mop it up to correct pH. I'll draw the chemical equation for the phosphate buffer system. So here we can see the monohydrogen phosphate ion can accept the proton and mop it up to correct our pH. This is a reversible reaction, so we can also release and donate protons when our blood becomes too alkalotic, so we can start shifting back towards this direction. We also have protein buffer systems. So here I've drawn a structure of an amino acid. So when the pH rises, the carboxyl group here acts as a weak acid, and it can donate this proton here into the solution and therefore correct the pH. Alternatively, if the pH falls, the amino group can act as a weak base and mop up and become protonated to correct the pH, so we can accept a proton. We also have the hemoglobin buffer system, which acts intracellularly. So deoxyhemoglobin can bind to proton, which is abundant in metabolizing tissue, where hemoglobin drops off oxygen and it carries back these protons to the lung, where it then releases the proton to make space to then rebind to oxygen. So finally, we have the bicarbonate buffer system, which is abundant in the ECF. So protons, such as the one dropped off by hemoglobin in the previous example, can bind to bicarbonate, a weak base. This causes a shift in equilibrium in this direction, because naturally the body likes to be balanced. It doesn't want too much of this. So the equilibrium shifts to the left, and this causes increased production of CO2 and water. And the CO2 can be exhaled, and that corrects our pH. On the other hand, let's say we held our breath. We are retaining CO2 as we are not breathing it out. Well, because there is excess CO2 here, this will shift the equilibrium to the right-hand side here, causing an increase in protons, making our blood more acidic. We can work out the pH of our plasma at normal body temperature using the Henderson-Hasselbalch equation. I have taken some time to derive the equation on the left, so please pause the video if you're interested to see how to derive the equation. Importantly, we should consider the ratio of bicarbonate ions to partial pressure of CO2, which will give us our pH. So 4 scenarios can essentially occur. We can have an increase or decrease in bicarbonate, or an increase or decrease in the partial pressure of our CO2. So an increase in our bicarbonate concentration will cause an increase in our ratio. So our overall pH will increase. You can try this on your calculator by just plugging in random values of bicarbonate and PaCO2 and see what happens to the overall value of our pH. And as our pH then increases, this will make more alkalotic plasma. A decrease in bicarbonate concentration will decrease our ratio, so pH will decrease, and we will have more acidotic plasma. An increase in the partial pressure of CO2 will cause a decrease in the ratio, so pH will decrease, and our plasma will become more acidic. And finally, a decrease in PaCO2 will cause an increase in this ratio, so an increase in pH, and we'll have more alkalotic plasma. Bicarbonate changes suggest metabolic pathology, and PaCO2 changes suggest respiratory pathology. So we can collect an arterial blood gas, or ABG for short. This is where we painfully go into a patient's artery and sample their arterial blood to give certain readings for bicarbonate, pH, PaCO2, etc. And using these values, we can work out what is the pH of the plasma, and we can work out whether it is metabolic or respiratory pathology that is the culprit. So let's do a few examples. Our first case is a patient who is a smoker. We've obtained his ABG. Can you find out what is wrong? Please pause the video to have a go. Okay, welcome back. We will go through it together. So firstly, the pH is lower than his normal range. He is in acidosis. We can see that when PaCO2 is raised, this will shift the equilibrium by law of mass action to the right, so more protons is generated. This is what is making his blood more acidic. As CO2 is raised, this suggests that this is driving the acidosis, and the respiratory pathology is the main culprit. Note that the bicarbonate has increased out of it, and this is an attempt to basically compensate, to accept these protons and compensate for the acidosis. So we say the patient is in respiratory acidosis with partial metabolic compensation. We say partial compensation because although the bicarbonate has increased to compensate and mop up the protons, the pH is still acidotic, so it hasn't fully compensated. The patient is hyperventilating. We have obtained an ABG. Please pause the video to have a go at this example. Okay, let's see how you got on. This time the pH is raised. So we say the patient's plasma is alkaline. We notice that their PaCO2 is low. So this must be causing the raised pH. If we have low PaCO2, the equilibrium will shift in this direction to generate more CO2. This will deplete the patient's hydrogen ions and therefore cause a rise in pH. The bicarbonate has also dropped a little to compensate for this rise in pH, so less protons will get mopped up. This is respiratory acidosis with partial metabolic compensation. This patient appears to have overdosed on some pills. Here is his ABG. Please pause the video to see if you can find out what is wrong. So welcome back. The patient has a low pH, so they are acidotic. So what is the culprit? Well, the PaCO2 is low. However, we would expect a low PaCO2 to cause alkalosis, not acidosis. So this cannot be respiratory in origin. We can see that the bicarbonate ions are also low at 15 millimoles per litre. So low bicarbonate will shift the equilibrium towards the right in an attempt to generate more bicarbonate ions. However, this increases the amount of protons as well. This increased amount of protons in the plasma therefore causing a decrease in pH. Therefore, this is metabolic in origin. This is a metabolic acidosis with partial respiratory compensation. We say there's partial respiratory compensation as some of the PaCO2 has basically been blown off in an attempt to correct the body's pH. This patient has been vomiting. This is the final case. Let's see how you get on. So the pH is increased. This is alkalosis. The PaCO2 is within normal range, so we know this cannot be causing a change in pH. The bicarbonate, however, is raised. So this excess bicarbonate is basically mopping up these protons and shifting the equilibrium to the left. So there is reduced protons now, and therefore an increase in pH. This is metabolic alkalosis. There is no respiratory compensation this time as PaCO2 is within normal range. If we suspect our patient has metabolic acidosis, we can go one step further and calculate the anion gap. And this will give us more clues as to what is the cause. Our body is electroneutral with cations equal to anions, i.e. positive charge equal to negative charges. We can use this equation to calculate the anion gap. Now, we don't measure all charged ions in this equation. We just are concerned with potassium, sodium, bicarbonate, and chloride. So there are a lot of unmeasured cations and unmeasured anions that aren't accounted for. So essentially, the anion gap is the difference between the unmeasured cations and the unmeasured anions. So from about this line to this line. And the normal range is between 8 to 14 millimoles per litre. We can have a metabolic acidosis with a normal anion gap. And a few causes of these are gastrointestinal causes, such as diarrhea causing a loss in bicarbonate or renal tubular acidosis. You might be thinking, if you have low bicarbonate, wouldn't the anion gap increase? Well, no, because actually the chloride increases to compensate, and we have a normal anion gap in the normal range. Albumin is an anion. So what would happen if we had low albumin or hypoalbuminemia? Well, we would have less unmeasured anions. So actually, we would have a low anion gap because our line would come up to about here. Let's imagine we ingested acid such as methanol. Well, methanol is an unmeasured anion. So our unmeasured anions will actually decrease. So this gap will instead increase. So it will come down to here. Our unmeasured anions will increase. The anion gap will increase. A few examples of a raised anion gap acidosis are lactic acid, ketones, uric acid, and just acid poisoning. On this slide, I've listed causes of different ranges of anion gap. Please pause and have a read. Let's go back to our patient who has taken some pills and has metabolic acidosis. Let's calculate the anion gap for this patient. So it would be, I'll say Ag anion gap is the concentration of sodium, so 135, plus concentration of potassium, plus 5.2, minus the concentration of bicarbonate, plus the concentration of chloride, so plus 15. So if you plug that into your calculator, that gives us 25.5 millimoles per litre. Now this is outside of our normal range. Our normal range was, the upper limit was 14. So this patient has a raised anion gap acidosis. So this patient has actually overdosed on aspirin, which is actually a salicylic acid. This is what is causing the high anion gap metabolic acidosis in this patient. So thank you for watching. Please visit our website www.jctuition.net for more free resources and videos.